Major advances in science are rarely the result of a lone genius, but behind great achievements are inspiring stories of remarkable individuals. Since 1899, the American Physical Society has worked to advance and diffuse the knowledge of physics for the benefit of all. APS honors are how we, as a community of physicists, recognize and celebrate those who further this important mission through their work and through their lives. Early career scientists are a critical piece of our community. They bring new ideas and perspectives to the table, and sometimes even transform the direction of an entire specialty area of the physics discipline. The George E. Valley Jr. Prize recognizes an early career individual for outstanding scientific contributions to physics that has significant potential for a dramatic impact on the field. The 2022 recipient is Andrew Lucas for pioneering contributions to developing the theory of hydrodynamic transport in interacting electron fluids.
It was a very specific sort of series of life events that turned me towards physics. In my junior year of high school, I participated in the US Physics Olympiad. After that experience, I sort of thought, well, maybe I should take physics more seriously. I really want to do physics sort of for a career. I had a pretty direct route. I knew that was going to be my major, and I took lots of classes. My undergrad mentor, Xiaoliang Qi, right as he actually got to Stanford, he really took me under his wing and advised me, and so that was really meaningful. There was a emeritus professor, Sandy Fetter, who was looking out for me, trying to get me more involved in the department doing research. I think it was really in 2015 that myself, my advisor, and other groups sort of started to take the idea of electron hydrodynamics seriously. And all hydrodynamics is the theory of what happens when you take many, many particles, conserving these same quantities, and you allow them to interact and collide off of one another. And you ask what happens if you zoom out, and you look not at individual collisions, but at the macroscopic many-body dynamics as a whole. A good analogy to have in mind is that we don't fly airplanes successfully because we model each of the individual molecules of air that bounce off of the wings. Instead, we recognize that the air moves as this collective medium, and we only need a few things like density and temperature and velocity. And just knowing those few things is sufficient. Just like for the plane, we don't need to calculate what each molecule is doing. We can instead just calculate the collective fluid flow over the wings. Our inspiration was that the same thing would also be true in the electron fluid. You wouldn't need to keep track of every single electron as it bounces around inside of this crystal lattice of atoms, but instead you could just keep track of the collective motion of the electrons. Part of the joy in doing physics is that you don't have to know the details about how every single thing works, because with just a few of the building blocks, you can really piece everything together. I wouldn't describe sort of taking on challenges in physics as zero-sum, like if you're not successful, then it was all a waste of time. I think that when you approach a difficult problem, it's often the case that even if you don't solve the original problem you were looking to solve, you've still learned a lot of really valuable things in the process. You can think of working in theoretical physics as sort of like hiking or climbing one of the mountains behind me, that you can kind of see your way up to the summit. Although maybe you can't see the summit directly, you just sort of know whether you should be going up or down. But there's many paths that you can take to get there. And many people, may reach that same place, but have taken different paths. Part of the joy in working on these problems has just been the ability to work with so many different types of physicists and interact with so many different types of physicists, to have them all come together to the same conference and talk to each other and share ideas. That's been the most enjoyable part of this.
Having a productive research career is itself an incredibly time-consuming endeavor. On top of this, some physicists go beyond their immediate research community to serve as influential mentors and teachers, or to reach the broader public as effective communicators. The Julius Edgar Lilienfeld Prize recognizes outstanding contributions to physics and exceptional skills in lecturing to diverse audiences. The 2022 recipient is Chang-Ki Jung for outstanding contributions and leadership in experimental neutrino physics, and for outstanding teaching and outreach, especially on the physics of sports.
I remember something like 6 years old, and I told the people that I want to be a professor. I'm not sure I knew what professor really meant, but you hear about things, and I want to be a professor. I grew up very poor. My family was very, very poor. The schools I went to was very poor, so I didn't have so-called role models any. But nonetheless, I was sort of naturally got interested in, I think it's a lot of other human beings do, that origin of time, where's how time began, and about the universe and such. Still working on it. I don't think I have answered those questions. I really didn't have that kind of mentor when I was younger. However, I did have the people kind of indirectly, they didn't mentor me, but I get to know them. One person, he's arguably probably the best physicist in the history of South Korea. His name is Ben Lee. When I was a freshman in college, Ben Lee came to Seoul National University. He gave a colloquium, and that itself was just cool. So we were all kind of mesmerized about it. And then I had the pleasure of meeting Maurice Goldhaber. He is, I will say, another legend in our field. And Maurice Goldhaber is the first person who experimentally determined how long protons can live. I was very much got into this question about protons. Does the protons ever die? And then that question is the one actually led to my current research about last 30 years. Neutrinos generally were nuisance background for proton decay search. But then we couldn't find the proton decay, so therefore we changed our attention to neutrinos. So one of the experiments I was heavily involved in, the Super-Kamiokande, K2K, and the T2K, those are the main experiments. One of the biggest things was that we discovered neutrinos oscillate. There are three types of neutrinos: electron neutrino, muon neutrino, tau neutrino. One of those interviews I had with the LA Times, I used the knowledge of ice cream for neutrino flavors. Let's say your muon neutrino is chocolate ice cream, and then you make a chocolate ice cream, you throw it across the country, and then when you receive the other side, it turns into vanilla ice cream. This actually happens in neutrinos. We do many experiments, we make breakthroughs, we understand more things. However, I consider this is that we are, building little sand towers. Towers get bigger and bigger, but still, it's a long way to go. Physical sports, I offered in 2003. I know I will be studying and teaching physics all my life, but I have interest in arts and sports. And then I realized that everything what we do in the sports is essentially classical mechanics. What's the difference between four-seam fastball and two-seam fastball and changeup? Four-seam fastball is not only stays more straight, it actually goes faster. Now, four-seam fastball thrown with an underspin, it experiences something called a magnetic force, which lifts the ball from below to upward. And so magnetic force is compensating the gravity large extent. That's why ball does not drop as much as other balls. As you are better, when you see a 100 miles an hour four-seam fastball, it appears to you ball is almost rising. But that's an optical illusion because the pitcher mound is higher up, and then ball doesn't drop as much as other balls. As a lecturer, as a professor, the way I see it is that no matter what topic I teach, as you walk in the classroom, essentially you have to consider yourself as a performer. So you have to know the level of students and then how to get their attention. But most importantly, you need to able to convey the enthusiasm. And then students can see that. That is like pleasure. That's the really pleasure of his life as being a professor here. And that's the pure joy of or being a professor. And in fact, it's the joy of my life.
The APS medal is truly the Society's highest honor. With this prize, we recognize an individual with research accomplishments, typically over a lifetime, that have transformed a field of physics or even multiple areas of physics. It is a celebration of those dedicated to scientific inquiry and the pursuit of knowledge. The APS Medal for Exceptional Achievement in Research recognizes contributions of the highest level that advance our knowledge and understanding of the physical universe in all its facets. The 2022 recipient of the APS Medal is Elliot Lieb for major contributions to theoretical physics, so obtaining exact solutions to important physical problems which have impacted condensed matter physics, quantum information, statistical mechanics, and atomic physics.
Well, as a kid, starting with about the age of 10, something like that, I became interested in doing experiments with electricity and also woodworking. Part of this curiosity was inspired by my uncle that I mentioned, who had this bookshop. He had a huge collection of Japanese prints, and I fell in love with these prints. When I entered MIT as an undergraduate, as a freshman, I wanted to be an electrical engineer. The reason I switched from engineering to physics was I fell under the influence of my freshman year instructor. His name was Matt Sands. The first thing you learn in physics is mechanics, and I just didn't get it. He was very patient, and he somehow felt that I was worth following. And eventually I did understand it. And he got me to understand that this was really a beautiful subject. And so I decided I wanted to be a physicist. Science is an international enterprise, and I saw it in several ways. And when I finished my degree, I decided I would go next to Japan. I learned Japanese and at least enough to get around. It was a wonderful, fantastic experience. Just after I got my PhD, I realized, I have to say this frankly, my thesis was not very good. It was okay. And I thought about joining the State Department as a scientific attaché, but I did not do this. Otherwise, it was I just kept going. Maybe I was not really any good at anything else. So I don't get discouraged. I just wait for the next tsunami to. Once in a while, one is lucky and one produces a really good paper, which you know is important even if nobody else knows it's important. And there have been papers like the strong subadditivity of entropy. That's one. I worked for 2 years on that all by myself. The other was this ice problem. The other thing was the stability of matter thing and why that works. These were high points, really high points. The year in which I solved this ice problem was 1968. A water molecule is one oxygen atom and two hydrogen atoms, H2O. And the oxygen atoms in the ice sit at a nice lattice, which you can see and measure. The hydrogens don't. They're sort of wobbly. And this wobble never goes away. You can estimate that the number of configurations, number of possible states of the ice would be with all possible wiggles. That's the entropy. What remained to be done was to actually prove this. I mean, actually calculate this number. So the number of ways you can put in these hydrogen atoms in such a way that at every point where there's an oxygen, there are two on the close side and two on the far side. That's a tough problem. And I solved that. The answer was 4/3 to the 3/2. Incredible, because I did it on a weekend. You asked me how I felt, that's how I felt. If I could start all over again, what would I tell a young person at this age? I would say, don't give up. If you think you can do something, just do it. Physics is made up of many parts, as we've come to understand. It's not. It used to be thought that there's one genius who starts everything. It doesn't work that way, if it ever did. Physics is a big enterprise with many people doing various things, being held together by a common interest in science. And it's important to have scientific institutes like the American Physical Society that bring all this together and publish journals and so on. And bit by bit, these different pieces interlace and interlock and produce, at the end of the day, something that's of value to the common good.